So this is our second video on equirectangular spherical perspective and how to draw it. Last time we learned what I call the sliding grid method. Given two arbitrary points, I taught you how to trace the equirectangular line segment that joins them using a grid like this and some tracing paper. If you haven't seen that, then please check out that video, as from now on I will assume that you know how to do that. Now, since we learn how to draw these lines by hand, I suppose you won't mind if now I do it on the computer, just because it is faster that way and easier for you to follow what I'm doing, so you can focus on the geometry rather than the manual part, which is slow to perform and it's hard to see on camera sometimes. But mind you, everything we will do can be done by hand by the sliding grid method from last time. Okay, so to draw these lines, I'll be using my own drawing program. It's a little toy program I made for my workshops a couple of years ago, and I've been developing it on my spare time. It's called Sketch 360. You can get it for free on my website, link below, or you can just ignore it and draw by hand. Beware, it's a very experimental program, has no frills, and probably has a lot of bugs. It's free, and you get what you pay for. Anyway, let me show you how it works. It has two main features: a grid that you can slide left and right, so it's your usual equirectangular grid, although not quite usual. You see, it's a bit different, and I'll talk about that later. The second main feature is that you can draw automatically any equirectangular line between 2 points. So you see, I'm selecting 2 points here, and when I draw with a mouse or a pen, the line that gets drawn is snapped onto the equirectangular line that joins the 2 points. So you see, this is the same. These are the same lines that you would get if you used the sliding grid method to trace the lines, like we did last time. For instance, just notice that the line between these 2 points is just one of the lines that you would find if you slid the grid to join these 2 points. So it's the same line. Same thing here. It's just a line that we found last time. Okay, so this is just a much faster way to do it. So you basically have 2 keys, N and M. You press N to select one point, M to select another, and you just join them by drawing in any way between the 2 points. You can also press V to draw verticals. Okay, enough of that. As I said, this is just a quick way of doing what we could do with the sliding grid method using tracing paper, which is what you will do if you're doing urban sketching on the street. Now, the first thing that I wanted to show you today is that the grid we use, let me just clear this up, okay, and center. The first thing I wanted to show you today is that the grid we used last time was quite the overkill. I mean, let me show it to you again. So yeah, this was the grid that we used in order to draw by hand using the tracing paper. And as you can see, it's very busy. This one is much cleaner. It's easier to see what you're drawing. And of course, this is what generates the other one. This usual grid is just 8 copies of this one. Okay, you take this segment, this part here with the curves from left to right, and you just reflect it across the horizon, and you get the downward part here, and then you just take all of this and you center it on the right point, on the left point, and on the back point, and you get this messy grid. This grid here is convenient, although it's so busy that it can confuse you. It's also convenient to draw by hand because curves are more available. You don't have to move around the grid so much. You don't have to invert it. This one, it has pros and cons. You can also try to use this one to draw by hand, but then you have to do a lot of flipping around with grid. But if we're drawing on the computer, this has only positive sides. Okay, it's much easier to see when I draw an equirectangular line. It's much easier to find the line by sliding if I use this grid than if I use the other one, where it can get pretty confusing with all those lines around. So this is one advantage of doing these demonstrations on the computer. Okay, but enough with the program. Let's go to today's tutorial. So last time we talked about perspective division. I gave you a rectangle, which could be a segment of a wall, and then I showed you how to divide it in half. Okay, let's review that and then continue on to what I call perspective multiplication. So let's start by choosing a vanishing point on the horizon anywhere we want. Let's say right here. You press N to choose a point, and now we slide the grid so that we center it 90 degrees away from the vanishing point. Okay, right here. And now we're going to pass a line that vanishes here and passes somewhere in front of us at a certain height, let's say 50 degrees. So we could actually, with this program, we can read here the bearing and the elevation as we move the cursor, but let's do this as if we were drawing with our sliding grid on tracing paper. So we use the grid by setting the edge of this family of curves here. We search for the height we want. Let's say we want 50 degrees up. So this is 5, 10, 20, 30, 40, and 50 degrees. So this is a line that vanishes to our right, 64 degrees to our right, and passes with maximum elevation, that is with apex, at 50 degrees. So we trace that line. Let's press plus to have a bigger brush. Okay, so that you can see better what I'm doing. Okay, so we have this line, and if this is a vanishing point on the horizon, then the line will again hit the horizon 180 degrees to the left at its other vanishing point. In spherical perspective, every line has exactly 2 vanishing points. So let's suppose we want another line passing under the horizon with the same vanishing points, and let's say 33 degrees elevation under the horizon. So 10, 20, 30, this is more or less 33. So I press M to choose a point, and I pass a line, and it has the same vanishing point here that I have set. And so I press N here and M here to choose my two probe points, and I pass another line that will vanish necessarily also at this vanishing point. So we have two lines in space that we know are parallel because they have the same vanishing point. And because they're parallel, this could define, let's say, a wall going from somewhere on my right to somewhere on my left. Now, let's define a section of this wall. Let's say from the apex here, from the highest point, we go 20 degrees to our left. See how we're using the sliding grid to make our measurements. I press V to draw a vertical. Okay, and the section of the wall goes 40 degrees, let's say 20, 30, 40 to our right. Okay, so this is a section of a wall. And now recall that last time we learned how to find the center of this wall by doing what I called perspective division. So press N here to choose this point and M to choose this one. So two corners of this rectangle, and just join them with an equirectangular line. And again, do the same for the opposite diagonal. And where these diagonals meet is the center of this section of the wall. And it's pretty easy to understand why if we look at this from an orthographic perspective. I'll just press F here to free draw. So if I see this in orthographic view, just look at it like this. What do I see? Well, if I'm looking straight on at this, then obviously if I do a big X right here, by symmetry, where these two lines meet is the center of the wall. And that's just what we did here, nothing more. But so we have the same thing in perspective. Now, if I pass a horizontal here that is a parallel to the top and bottom of the wall, and a vertical, and then I do another X right here, well, this is a rectangle that has the same proportions as this big one. Okay, so I'm further subdividing the rectangle, and I could do it again and again to get a uniform division of this rectangle that would work as a grid wherein I could locate with any precision desired any pattern or point that I wish to locate. Okay, so here, exactly the same thing that I have done. I set one point here, the vanishing point, another point here, press N here and M here, and I pass this horizontal, which is this one here on the orthographic view, and the vertical, I can obtain it because, as we have seen last time, verticals project as verticals in equirectangular perspective. And so I have this subdivision, and then I can continue like this with this line here. Okay, so I can subdivide further and further to get more and more precision. But in the same way that I subdivide, I can now do perspective multiplication. Suppose I want another section of the wall that's just as large as this one. How do I obtain it? Well, here it's pretty easy to understand. Suppose I take this point here and this point here, and I pass a line between these 2 points. Well, when this line hits the floor, it defines a rectangle just as big as the previous one. Why? Well, it's really easy to see that this angle is equal to this angle, and this angle here, which is a right angle, is equal to this angle here. And because this is the midpoint of this vertical, then this segment here is just as large as this segment here. So we have angle, side, angle, and angle, side, angle. And since they are equal, then the whole triangles are congruent. They are a copy of each other. Okay, so this triangle is congruent with this triangle, and therefore this side is congruent with this side, and therefore, because this side is in common, this rectangle is congruent with this rectangle. Okay, that is, this is a copy of this. So doing the same in perspective, I take the corner here and the midpoint here, and I join them by an equirectangular line, and where this line hits the floor, I pass a vertical, and it is guaranteed that this rectangle, this section of the wall, is congruent, that is a copy of this original section of the wall. And by repeating the same reasoning, if I take this corner here and this midpoint here, and I pass a line here, and I hit the floor with it, well, if I take a vertical here, this vertical defines a new section of the wall that is just as large as this one. And I can repeat it, and so on, indefinitely. Let me do another one here, and we'll stop. Of course, I can do this backwards also. If I take this point here and this midpoint here, and I pass a diagonal like this, and where it hits the top, I pass a vertical, then I get a section of the wall that is a copy of the original section. Okay, and of course I can continue indefinitely to the left. As far as I wish. Okay, so this is really important because if you're drawing in equirectangular perspective, or in fact in any spherical perspective, it can get pretty confusing to your intuition how big things are. Okay, you need to have some method to determine how big these divisions must be, and next time I'll show you a much more complex case than this one to really stress that point. But for now, I think we have done enough. Now we know how to do basic perspective arithmetic, that is multiplication and division. And I'll just end by showing you the result of what we did in VR. And for that, we'll press S, which saves the picture in this program. So just press S, it's a quick save. It will save 2 copies of your drawing, one in TIFF, which is better for editing later, and one in JPEG for visualization. And you can use this JPEG to send it to Facebook or Flickr to see it in VR, or you can see it on the desktop with a free program called FSP Viewer, and it will show you the drawing like this. Oh, by the way, once you're done with the drawing, you can press G here to switch the grid on and off to see better what you've done. And but here in VR, you can see the result and check it visually, no longer in spherical perspective, but in linear perspective, or in anamorphosis, so to speak. So here you see our original section of the wall. Okay, let me zoom out a bit. And as you can see, we have done several copies of it, which are the same size. Okay, there's a bit of so-called perspective deformation here because of the wide angle at which we are seeing this, but you can check that it's the same size. Okay, it's a uniform division of the wall. Okay, so that's all for now. Next time, I'd like to show you a different method for doing the same task. And you see, here is an example that I've shown you before. This is one that I drew with the sliding grid method from observation. And I used, it's a situation similar to the one we've treated today. We have this regular division of a wall determined by the intervals of these columns here. And using this method that I taught you, I could just measure this first section here and then multiply it. But in fact, I have used a slightly different method that is more elegant than the one I've told you about today. And I will teach you this other method next time, probably. And in fact, this drawing contains much of what I will teach you in future. There are several elements here. First, the perspective arithmetic, and then which is used to solve this problem here of the columns. And then here you can see another classical problem of a tiled floor, tiling uniform floors is drawing uniform tilings of a floor is a classical problem of perspective, and we'll go through that also. Here you can also see another classic problem, which is projected shadows. Okay, you have this shadow of this column projecting here on the floor and then against the wall, and we will also speak of that later. But for now, I hope you enjoy this, and this is all. See you next time.